Welcome back to AGRON Infotech. This is our first clustering video, and today we build the one idea that sits underneath every clustering algorithm: distance. Clustering is simply grouping observations that are close to each other. So if we understand distance, we understand the foundation of clustering. I start by loading Tidyverse because it gives us clean tools for data handling and plotting. Now I load the Wholesale customers dataset from the UCI repository. I use a small helper function so the script works in two situations. First, if the CSV file already exists in my folder, the code reads it directly. Second, if the file is not there, the code downloads the official zip file from UCI, saves it to a temporary location, unzips it, searches for the CSV inside, and reads it into R. While reading the CSV, I keep the argument that suppresses noisy column type printing so the console stays clean. Now I preview the dataset structure using a quick glimpse. The output tells us there are 440 rows and 8 columns. We can see 2 identifiers, channel and region, plus 6 spending variables like fresh, milk, grocery, frozen, detergents and paper, and delicatessen. Then I run a summary to understand the range of values. This output is important because it shows the spending variables have very different scales. For example, fresh can go up to well over 100,000, while some other variables can be much smaller. That difference is going to matter later when we discuss scaling. Now I move into the distance intuition with the simplest possible case. I take the first 2 customers, keep only fresh and milk spending, and I add an ID column so we can label points on a plot. When I print this small tibble, it shows customer 1 has fresh spending of 12,669 and milk spending of 9,656, while customer 2 has fresh spending of 7,057 and milk spending of 9,810. Next, I visualize these 2 customers in feature space. The scatter plot appears with fresh on the x-axis and milk on the y-axis. Each customer becomes 1 point. In this plot, customer 1 appears far to the right because fresh spending is larger, while customer 2 appears more to the left. Their milk spending is similar, so vertically they are close. The labels 1 and 2 help us see which point is which. Now I compute the Euclidean distance manually, just once, so the idea becomes real. I take the difference in fresh, the difference in milk, square them, add them, and take the square root. The output gives a distance of about 5,614. This number is the straight line distance between the 2 points on the chart. So visually, a larger separation on the plot means a larger distance value. Now I confirm that result using the dist function. In dist, I specify the method argument as Euclidean, so it uses the same distance we just calculated manually. The output gives the exact same value, about 5,614, which confirms our understanding. At this stage, we have proven that distance in clustering is not mysterious. It is a direct measurement in feature space. Next, I add a 3rd customer and compute a distance matrix. I select customers 1, 2, and 50, again using fresh and milk. When I print this tibble, customer 50 has fresh spending of 4,967 and milk spending of 21,412, which is a very different milk level compared to the first 2. Then I compute the distance matrix and print it as a full matrix. The diagonal is 0 because every observation has 0 distance to itself. The distance between customers 1 and 2 remains 5614. The distance between customer 1 and customer 3 is about 14,054, and between customer 2 and 3 it is about 11,789. That tells us customer 3 is much farther away from both of the first 2 customers, mostly because of the large difference in milk spending. Now I scale this idea up slightly with 6 customers and 3 features: fresh, milk, and grocery. I print those 6 rows so we can see realistic variation across multiple spending categories. Then I compute the full distance matrix. This output is larger, but the meaning is the same. Every number represents how far one customer is from another when we consider all 3 spending features together. This is exactly the object that many clustering algorithms rely on internally. Now we reach one of the most important lessons in clustering: scaling. I create a small demo using fresh and detergents and paper spending because those variables can live on very different ranges. First, I compute distance without scaling. The output shows distances like 5646 and 6372, which look large because the raw units are large. Then I scale the variables and compute distance again. Now the distances become values like 2.15 and 2.66. The key point is not that the numbers are smaller. The key point is that after scaling, each feature contributes more fairly. Without scaling, whichever variable has the largest numeric range tends to dominate the distance, and that can quietly distort clustering. Finally, I show how we handle categorical variables like channel and region. Because Euclidean distance expects numeric variables, we cannot feed raw categories directly into dist. So I first convert channel and region into factors. Then I select one example from each channel by region combination, so the demo is easy to interpret. When I print this table, I can see the 6 combinations across channel 1 and 2, and regions 1, 2, and 3. Now I convert these categories into dummy variables using a model matrix. I explicitly remove the intercept term, so we only get clean indicator columns. The resulting table has columns for channel 1, channel 2, region 2, and region 3, and each row contains zeros and ones describing that category combination. This is now a binary feature representation. Next, I compute binary distance on these dummy variables. This method behaves like a jacket-style distance for binary data. In the output matrix, a value of 0 means 2 rows share the same category pattern, while larger values mean more mismatch. For example, rows that only differ by region have smaller distances like 0.5, while rows that differ by channel have larger distances like 1.0. This is the correct way to measure similarity when the features represent membership rather than magnitude. At this point, you have a full distance toolkit. You can compute Euclidean distance for numeric features. You understand why scaling changes what similarity means, and you can handle categorical variables by converting them into dummy variables and using binary distance. In the next video, we take these distances and build real clusters using hierarchical clustering. We create dendrograms, compare linkage methods, and learn how to cut the tree into meaningful groups.